Welcome to qnawire.
So in this problem, we have been given a gallium atom, and we have been asked to write down the quantum number for each of the electrons in the gallium atom. So the atomic number of gallium atom is 31. So there are 31 electrons, and we are gonna go in steps for each of these electrons. So let's say we have N, L, Ml, and Ms. Uh, in the first state, when N is 1, L can, so let me just write that for any value of L, N, L can take values from 0 to N minus 1, okay. ML, for any value of L, ML can go from plus L to minus L, and MS can be 1 or so we are going to use these equations, quantum to write down all the quantum numbers for the electrons for each electron in the gallium atom. So let's say that when n is 1, L can only be 0, which means that ML has to be 0, and MS can take two values, 1 half, and we have this minus 1 half. So two electrons are done. We have to write now for the remaining 29 electrons, which is a daunting task. So when n is equal to 2, L can be so when n is equal to 2, L can be either 0 or it can be 1. So let me just write, when n is 2, L can be 0 or 1. So let's say that when L is equal to 0, ML can only be 0. So when L is 0, ML can be 0, but MS can be two values. So these two values. When L is 1, ML can be minus ML can be minus 1, 0, or 1. So let's say that we first write down for minus 1. So for minus 1, we have this N, L, ML, MS. So we have minus 1, then we have spin minus 1 half for uh, the electron, and then when L is 1, that's now done. When L is 1 and ML is 0, we have plus 1 half, minus 1 half for electron. Let's move on to the next slide. We have N, L, ML, MS, and when N is equal to 2 and we have L is equal to 1, so that only remaining value for ML is now 1. So we write down quantum numbers for these, minus 1 half. So in total, we are done with now 10 electrons, 3, 4, 5, 6, and 8. Yeah, so we have to write uh, now for remaining 21 electrons. Now the only value that n can take is 3 now. So when n is 3, L can be 0, 1, 2. So let's consider when L is 0, ML can only be 0. So we have MS 1 half, and then when it is 0, 0 minus 1 half. When L is 1, when L is 1, ML can be minus 1, 0, or 1. So let's consider for minus 1, we have minus 1 half, 3, 1, minus 1, this one corresponding to minus 1 half. Then let's write down when L is 1, ML is 0. So for ML 0, we have again two quantum numbers corresponding to 1 half and minus 1 half. And when L When L is 1, it's going to minus 1 half. Now let's move on to the next one. N, L, ML, MS. So we are done with L. So we have n is equal to 3, we are done with 0 and 1. Now let's move on to 2. So when L is 2, ML can take values from minus 2 to 2. So let's say that this is minus 2. This is minus 2, so this is minus 1 half. And then we move on to the next one, minus 1, 1 half, 3, 2, minus 1. Then this is minus 1 half. Then we'll move on one step down, minus 1. Then after minus 1 we go to 0, 1 half plus 1 half, 3, 2, 0, minus 1 half. Now then we move on further up. So we go from 0 to 1, 1 half, 3, 2, 1, minus 1 half, and the only remaining value is now 2. When L is equal to 2, ML is 2, 1 half, and 3, 2, 2, minus 1 half. So now 28 electrons are done, and we just have to write for the remaining 3 electrons which are left. So we have now n is equal to 4. So L can take values 0, 1, 2, and 3. So let's write down for n is equal to 4. The first value is 0. Therefore ML value is 0. So we get 2 states for that, minus 1 half. Now for the last electron we can have L as 1. So ML can be anything. It can be minus 1. I'm just going to take 0 here. It can, so when L is 1, ML can be anything, minus 1, 0, or 1. So I'm going to take 0, and let's take the 1 half quantum number. So the last state is uncertain, it can be anything. Now then we move on to the next part, in which we have been asked which subshells are filled. So as we see, all of the subshells, 1s, 2s, 2p, 3s, 3p, 3d, and 4s are filled from part A. And the last electron, which is in 4p state, what are the possible values of total angular momentum for it? So p basically corresponds to L is equal to 1. So the orbital quantum number is L is equal to 1, and since this is an electron, so it has a spin quantum number as 1 half. So the possible values for uh, total angular momentum quantum number, total J, which is the total angular momentum quantum number, can be either L plus S, which is 1 plus 1 half, gives us 3 half. This is a very big problem. And it can be L minus S, 1 minus 1 half. So it can be either 3 half or 1 half. So we move on to the next part, part D. Now we have been asked to calculate, explain why the angular momentum of this electron also represents the total angular momentum of the entire atom. Now whenever any subshell is filled subshell means corresponds to 0, angular momentum for that subshell. So in this case, all of the subshells are filled except for 4p is not filled. So we write 4p is not filled completely. So completely filled subshell. Sorry for that. Completely filled subshells. So since 4p is not completely filled subshell, therefore the atom will have the total angular momentum of the 4p subshell, whatever angular momentum the 4p had. How could you use Stern-Gerlach experiment to determine value of j, whichever value of the j the atom has? So in Stern-Gerlach experiment, whenever an electron is passed through an inhomogeneous magnetic field, the magnetic field splits the states of the electron, which basically corresponds, the splitting corresponds to the spin of the electron. So in this case, instead of electron, we have an atom, and silver atom which has total angular momentum of 1/2 or 3/2. So if when j is 1/2, mj can take values either 1/2 or sorry -1/2. So if we see just two lines, then we can say that for two lines j is 1/2, whereas when j is 3/2, mj can take values 3/2, 1/2, -1/2, -3/2. So if we see four lines, we can say that the value for j is 3/2. So depending on the number of lines that we observe, we can determine the value of j.